This is the first lecture of week 7. In the previous week, we introduced the concept of weak convergence of probability measures and weak convergence of random variables through the corresponding pointwise convergence of distribution functions. So, there we had asked for the pointwise convergence to hold for the continuity points of the limit distribution function. Using such concept, we have seen some examples where such convergences hold. We have also remarked that we do not require the random variables to be defined on the same probability space. We can consider random variables on different probability spaces, even then they can converge in this notion of convergence. Moreover, we have seen tightness as a condition for this type of convergences to hold, or just to ensure that the limit function turns out to be a distribution function. We have also discussed another equivalent condition in terms of the corresponding pointwise convergence of the characteristic function. So, this was discussed earlier in Levy's continuity theorem. And in the final lecture of week 6, we have started looking at some of the equivalent conditions as part of the list of 14 conditions that we had stated earlier. In this lecture, the plan is to complete the proof of all these equivalences. So, let us continue the discussion using the lecture notes. So, we are looking at this weak convergence of random variables and of probability measures on the real line. Now, we go back to theorem 3 of our earlier week's discussion. So, there we had listed several equivalent conditions, in total 14, which we have stated to be equivalent between each other. Now, let us take a stock of what we have already covered and what else needs to be proved. In remark 13 and note 10 of our previous week, we mentioned that the statements 1, 2 and 13 are equivalent. For the rest of this lecture, what we do is that we think of these three statements as one group of statements which are all equivalent amongst themselves, and we refer to such a group of statements as group A. Now, let us move on and see some other equivalent statements of theorem 3. So, in the theorem 3, we had stated these two statements, number 9 and number 12. So, let us recall. So, number 9 involves limit inferior of certain open sets. So, if you choose open sets G in R and look at mu n of G, then the limit of that should be greater or equals to mu of G. So, here again we are following the same notational terminology as pointed out earlier in theorem 3 of our previous week. So, here we are given sequence of probability measures on the real line together with the Borel sigma field, and we are trying to think of mu as some kind of a limit measure. So, the 9th statement was about limit inferior of mu n's of G. Statement 12 involves this type of left open right closed intervals, and here we ask that if the measure of the boundary of the intervals is 0, then limit of mu n of these intervals should go to mu of the interval a b. So, this is statement 12. Now, here we want to show that statement number 12 actually implies statement number 9. So, to start off with, let G be some open set in R, and we want to look at lim_inf of mu n of G. Now, first, if G is open in R, then there is this nice structural property that there exist at most countably many intervals such that the intervals, the union of that gives you G. So, here additional properties of these intervals are like this, that the interval should be first of all open intervals, and they also should be pairwise disjoint. Now, in this decomposition that we are looking at, it can be shown that if G is open, then such a pairwise disjoint collection of open intervals can be found. Now, either they can be finite or they can be countably infinite, but either of the two. So, now just for our notational simplicity, we work with the case when the collection is countably infinite. If not, we have to reduce by taking the collection of intervals to be finite, and we will again enumerate them as number 1 to up to certain number n, depending on the cardinality of the number of intervals. Now, let us continue the case by assuming that we have countably infinite pairwise disjoint open intervals, and here we now start indexing by all positive integers. Now, let us apply Fatou's lemma and observe that limit inferior of mu n of g. So, if you replace g by the corresponding union of pairwise disjoint open intervals, we can write it as a summation. So, this is just by using countable additivity of the individual probability measures mu n. But now, we use Fatou's lemma here and push the lim_inf inside, but the effect is that instead of an equality, we will end up with an inequality. Alright. So, we end up with some kind of a lower bound of this limit inferior that we have started off in the left hand side. Now, let us fix some epsilon positive. Now, with this epsilon, choose some arbitrary integer alpha coming from our indexing set. Then what we do is that for our given interval I alpha, which is an open interval, we look at a left open right closed interval contained inside I alpha. So, let us try to visualize what we are trying to do. So, we are having some interval, open interval, which is I alpha, and then we are saying that we will look at a left open right closed interval, which we denote by A alpha, B alpha. Now, here we want some additional conditions on this left open right closed intervals. So, the first condition that we want is that the measure of this left open right closed interval should not be too far away from the original interval I alpha, and what we want is that this should satisfy this inequality, that first of all measure of the left open right closed interval is less or equal to measure of I alpha, but it should not be too far away by looking at this distance, or which is controlled by epsilon over 2 to the alpha. And moreover, by choosing A alpha and B alpha appropriately, we also would like to ensure that the boundary of this left open right closed interval should have measure 0, and all of these should happen in terms of the limit measure. So, that is all we are asking. So, here we are using the fact that the limit measure mu can put at most countably many points with positive mass. So, except those points, we are just looking at these A alphas and B alphas, and accordingly we are choosing such left open right closed intervals. But now, if you look at individually these left open right closed intervals, we can appeal to statement 12 and there we can pass to the limit. So, let us see what is happening. So, if you continue from the previous set of inequalities that we already have, we first observe that lim_inf of mu n of g, which we had on the left hand side of our previous calculation, that is greater or equal to this summation of lim_infs, and here it is important to note that for each alpha, mu of I alpha is greater or equals to mu of this left open right closed interval. So, we just appeal to that and write it as greater or equal to this lim_inf and their summations. So, that is how we get this step. But now, here since we are working with a left open right closed interval for which the boundary points are having mass 0 under the limit measure mu. So, this is actually the case when the limit exists, and therefore, the lim_inf also will match with the limit, and that will be exactly this quantity. So, therefore, we end up with this expression, and this step we are just performing, and this is happening to be an equality. So, a correction will be made in the lecture notes. But now, let us look at this summation of all these left open right closed intervals. Now, individually we have estimated that this measure of the left open right closed interval should not be too far away from the original intervals I alpha. So, therefore, if you plug in that lower bound that we have already assumed as part of the construction, we will end up with this much of an error at the end, and therefore, we have gone back to the original intervals I alpha. But now recall that I alphas were chosen to be pairwise disjoint and their union is just G. So, therefore, again use the countable additivity of the limit measure mu and write this summation just as measure of G. G is now an open set, and we also have minus epsilon. So, therefore, we ended up showing that for arbitrary epsilon positive, the limit of mu n of G is greater or equal to mu of G minus epsilon. But since epsilon can vary, we immediately have that the inequality as stated in 9 will hold. So, therefore, assuming 12, we have ensured that 9 will hold, and therefore, 12 implies 9. But let us see the consequence of this result, that 12 implies 9. What we have already discussed in the previous week is that in remark 14 and 15, we had established that 9 and 10th, these statements were equivalent. Moreover, either of these equivalent statements, meaning 9 or 10, also imply the 11th statement, which in turn implies the 12th statement. But now we are showing that 12 also implies 9. So, therefore, we have actually now proved is that 9 to 12, all these statements are actually equivalent. And now, to present our argument in a compact form, we now put these statements 9 to 12 as a group. So, these group of statements we will now think of as group B. So, remember earlier we had considered the group of statements 1, 2 and 13 as group A. We are now introducing another new group of statements, which is 9, 10, 11 and 12, and we have ensured that all these statements are equivalent between each other. So, now let us continue and see what other equivalent statements we can get. So, now what we do is that we go back to statements 3 and 4. So, just to recall these statements from our theorem 3 of previous week. So, statement 3 involves that we have for all bounded and continuous functions on the real line, the limit of the integrations with respect to all these measures mu n should be integration of the integrations with respect to the measure mu. So, this is the relation star, and recall the fourth statement that the star relation holds for a restrictive class of functions, which is bounded and Lipschitz continuous. So, we are now asking the equivalence between 3 and 4. Remember that as long as you are looking at bounded and Lipschitz continuous functions, they are in particular bounded and continuous. So, if the limit star holds for all bounded and continuous functions as assumed in the third statement, then immediately we will have the partial case involving bounded and Lipschitz continuous functions, and therefore, 3 implies 4. Immediate application of statement 3, and therefore, we have 3 implies 4. But we actually want to look at the convert statement now. So, here we look at the convert statement in the sense that we assume first that the fourth statement involving bounded and Lipschitz continuous functions is true, and we want to now prove the third statement. So, for that let f R2R be a bounded and continuous function. What can be shown is that we can approximate our continuous function f by a sequence of bounded and Lipschitz continuous functions such that GNs increase to f pointwise sense as n goes to infinity. Moreover, we can also show that Gn are lower bounded in terms of the supremum of the original function mod f. So, this is in terms of actually the L infinity norm of the given continuous function, which is assumed to be also bounded. So, this construction I leave it to you as an exercise, please check this. Now, assuming this fact that these Gns are all lower bounded by such a constant and they increase to this function f, we appeal to the monotone convergence theorem and conclude that limit of integrations of Gn will go to integration of f with respect to the limit measure. So, we are not changing the measures here, we are working with the limit measure. So, now for every fixed integer j, what we observe is first that if you now take this bounded and continuous function f, let us look at the limit inferior of these integrations with respect to each of the measures mu n. Then first of all, f is greater or equals to g j. So, that is by construction, and this is true for every fixed j. So, therefore, we get this inequality first, but for individual g j's which are now bounded and Lipschitz continuous, we know that the limit holds, and by our assumption statement 4 tells you that the limit must be integration of g j with respect to the limit measure mu. But now, let us observe that our left hand side of this expression, which involves integration of f, does not depend on j, whereas on the right hand side we have some expression involving j. What we do is that we let j go to infinity on both sides, left side is unchanged, on the right hand side we will end up with this limit. But now, we observe first that these g j's now increase and increase to f, and that is by our earlier observation this will go to integration of f with respect to the limit measure mu. And therefore, what we have is this double star relation which says limit of integration of f with respect to all these individual measures mu n is greater or equals to integration of f d mu. But now, let us replace f by minus f. Again, since we have assumed the original function f to be bounded and continuous, again we can replace it by another bounded and continuous function just by replacing f by minus f. So, now what we observe is that if we appeal to the double star relation and put minus f in the place of f, on the left hand side we will have minus lim sup as n goes to infinity of the integrations of f d mu n. So, that is appearing on the left hand side, and on the right hand side we will have this is greater or equals to minus integration of f d mu, and just by cancelling off the negative sign we will have the opposite inequality that integration of f d mu is greater or equals to lim sup of these integrations with respect to the individual measures mu n. But now, look at double star and triple star together. Here immediately we will say that since lim sup by definition is always greater or equals to lim inf, we immediately have that the equality must hold in the sense that first of all limit of f d mu n that should exist and that should match with integration of f d mu. But here f is some arbitrary bounded and continuous function, and therefore, we have the third statement, and we have ensured therefore, that third and fourth statements are equivalent. But now, we also want to connect other statements together with 3 and 4. So, recall that as we have used already, any Lipschitz continuous function is continuous, but moreover it is actually uniformly continuous. Again, any uniformly continuous function is also continuous. So, now let us recall another statement which is number 5 in our list. So, again we want that the limit of such integrations of such functions should hold for all bounded and uniformly continuous functions. So, then we observe certain implications. So, first we start with the statement 3 involving all bounded and continuous functions for which the appropriate limit star holds. So, then since any bounded and uniformly continuous function is also bounded and continuous, so therefore, the third statement implies the fifth statement. But again, as already pointed out, any Lipschitz continuous function is also uniformly continuous. So, therefore, any bounded and Lipschitz continuous function is bounded and uniformly continuous. Consequently, the statement 5 implies statement 4. But we have already pointed out that statement 4 is actually implying statement 3, it is in fact equivalent to statement 3, and therefore, we actually have the equivalence between third, fourth and fifth statement of theorem 3 of the previous week. Now, for the rest of the lectures, in order to refer to all these results, what we will look at are these group of statements now, which we introduced as the third group, group C, as third, fourth and fifth statements. So, we now have 3 groups. The first group A involved first statement, second statement and the 13th statement. Group B includes statement 9 to 12th, and now we have introduced another group C which involves statement 3 to statement 5. So, let us now include some other statements and let us compare them with the existing statements. So, we start with 7th and 8th statements. So, for that we first recall some basic definitions from real analysis. So, these are the definitions of lower and upper semi-continuous functions. So, we say a function defined on the real line is lower semi-continuous if for each point x naught on the real line you look at liminf of x going to x naught of the function values. So, if this liminf is greater or equals to the actual function value at x naught, we say that the given function f is lower semi-continuous. Similarly, we have another similar definitions for a function being called upper semi-continuous. So, here we are going to look at lim sup as x goes to x naught of the function values, but this lim sup should be less or equal to the function value at x naught, and if it holds for all x naught in R, we call it upper semi-continuous. Now, there are several interesting properties that connects lower semi-continuities and upper semi-continuities together with the usual notion of continuity. So, here what we first observe is that a function f on the real line is continuous if and only if it is both lower and upper semi-continuous. So, to check continuity, alternatively what we can try to check is that it is both lower and upper semi-continuous. Automatically the definition of continuity implies lower semi-continuity and upper semi-continuity. So, this is left as an exercise, please check this. Now, here is this another condition which connects lower semi-continuity together with the upper semi-continuity. So, the observation is very simple, that if I take a lower semi-continuous function, then minus of f must be upper semi-continuous. Conversely, if minus of f is upper semi-continuous, then the original function f must be lower semi-continuous. So, this connects lower semi-continuity together with upper semi-continuity. Now, we are going to use these identifications between continuity, lower semi-continuity and upper semi-continuity and observe certain implications. So, we first recall the statements number 7 and 8. So, in the statement number 7, we are looking at all bounded and lower semi-continuous functions on the real line, and we are asking for the integrations of f with respect to these measures mu n and looking at the liminf of the integrations. And if it so happens that this liminf is greater or equals to integration of f with respect to the limit measure, then we say that statement 7 holds. Similarly, we are going to also look at the 8th statement, which now involves the upper semi-continuity properties. So, here we are asking for all bounded and upper semi-continuous functions on the real line. So, here what we want is that we are asking for lim sup of these integrations, and we want that it should be upper bounded by the integration of f d mu. All right. So, here what we are looking at are two conditions, condition number 7 and condition number 8. Condition number 7 involves all bounded and lower semi-continuous functions, and for that we are asking for some kind of bound involving the liminf of the corresponding integrations. In terms of the upper semi-continuity, which is the 8th statement, we are asking for certain bounds to hold for the lim sup of the integrations. So, now what we want to say is that these two statements are related to each other. So, let us see. So, here what we go back to is the exercise 2. In exercise 2, we said that if I have a lower semi-continuous function, then minus of f is also upper semi-continuous. Then what we observe is that if we start with the statement number 7, then we have liminf of the integrations f d mu n as n goes to infinity, that is greater or equals to integration of f d mu. Now, this is given for all f which is bounded and lower semi-continuous. Now, take g to be a function defined on the real line which is bounded and upper semi continuous. Then what we immediately observe by using our exercise 2, that we will have minus g is bounded and lower semi continuous, and we can appeal to this function minus g and put it in as part of statement 7 in this previous relation. So, instead of f we now put minus g on both sides, and that is going to give us the relation which involves 8, because all we have to observe is that we rewrite this relation as minus lim sup of the integrations g du mu n as n goes to infinity, and that is greater or equals to minus of integration g d mu, but just cancelling off the minus sign on both sides we will end up with the opposite inequality, which is the statement 8 for all bounded and upper semi continuous functions g. So, therefore, 7 implies 8, and in a similar argument by again using exercise 2 we can show that the 8th statement implies statement 9. So, therefore, 7th and 8th statements are equivalent. So, we now look at further properties of lower and upper semi continuities. So, these are given in another exercise here. So, suppose I have a bounded and lower semi continuous function f defined on the real line, then you can construct a sequence of bounded and continuous functions such that the functions first of all are bounded between these two numbers, and moreover the bounded and continuous functions f n increase to f pointwise as n goes to infinity. This is similar in nature to the approximation that we performed for approximating a continuous function by Lipschitz continuous functions, but now we are using approximations of bounded and lower semi continuous functions by a sequence of bounded and continuous functions. All right, and here again the pointwise convergence holds in the increasing order direction. All right, and a similar statement is also true if you work with bounded and upper semi continuous functions. So, try to formulate the same statement and prove this. So, that is the exercise, but now we can use this exercise and we look at the implications between the third statement and the seventh statement. What we observe is that in the third statement we are asking for the appropriate limit to hold for bounded and continuous functions. So, therefore, what we do is that if we now take a general bounded and lower semi continuous function as is required in statement 7, then first approximate it by exercise 3 using a bounded sequence of continuous functions which increase to f pointwise. Then just by taking the appropriate limit, since the statements are true for all bounded and continuous functions as per statement 3, we will have the implication that the third statement implies the seventh statement, and this is an application of the again the monotone convergence theorem. So, therefore, what we ended up having is that the third statement implies the seventh statement. Note here that seventh and eighth statements both are equivalent as was already pointed out. We now connect another statement together with these statements that we have discussed, meaning the seventh and eighth statements together with 6, and here we claim that equivalent statements which are seventh and eighth, they both imply the sixth statement. So, let us recall the sixth statement here. So, here what we have in the sixth statement is that this limit is true for all bounded and measurable functions which in addition are continuous mu almost everywhere, meaning mu is the limit measure. We can find mu null set outside which the corresponding functions that we are considering are continuous, and here the functions are assumed to be bounded and measurable. So, there is no problem in defining these integrations with respect to the corresponding probability measures. Now, we are asking that the limit should exist and it should be equal to the integration of f d mu. So, this is the sixth statement. What we claim is that the equivalent statement seventh and eighth implies the sixth statement. So, let us see. So, what we do is that we start with a general bounded and measurable function f, which is continuous mu almost everywhere. Now, given such a function f, what we do is that we construct two other functions which are called the lower envelope and the upper envelope, and the notations for them are f lower bar and f upper bar. So, let us see how they are defined. The f lower bar, the lower envelope function, is defined as the pointwise limit inferior of these values as y goes to x, and f upper bar, the upper envelope of the original function f, is defined as the limit superior of the function values as y goes to x. Now, here since the original function f is bounded, then the lower envelope is still bounded. Moreover, it can be checked that by definition it is lower semi continuous. Similarly, the upper envelope function f upper bar is again bounded by definition, and moreover it is upper semi continuous. So, now if we assume the equivalent statements 7th and 8th, we can observe certain interesting inequalities. So, first observe that by definition the original function f falls between these two functions, the lower envelope function and the upper envelope function, and moreover since the original function is continuous, you can actually check that these functions agree mu almost everywhere. So, therefore, by assuming the equivalent statements, what we first claim is that integration of f should be first equal to integration of f lower bar, which is the lower envelope function. This is equal because the two functions agree mu almost everywhere. Now, f lower bar is bounded and lower semi continuous, and therefore, we can appeal to statement number 7 and write it in terms of this limit inferior of such sequences. Now, here we appeal to the inequality that f lower bar, that function is less or equal to f. So, therefore, we immediately have that this limit inferior is less or equal to limit inferior of the integrations of the functions f. Now, next we observe that limit inferior is less equals to limit superior of the same sequence. So, that is what we write, but now we observe that f itself is less or equal to the upper envelope f upper bar, and therefore, we can write it less equal to lim sup of f upper bar. But now, f upper bar, the upper envelope function, is bounded and it is also upper semi continuous, and therefore, we can appeal to statement number 8 and say that this is actually equal to integration of f upper bar. But now, f upper bar is actually equal to f mu almost everywhere. So, this is another statement that we have pointed out. So, therefore, these integration matches with the integration of f. But now, let us look at this set of inequalities that we just obtained. So, on the left hand side we started with integration of f with respect to the limit measure mu, and using all this less equal to inequalities in between, we have ended with the original integration once more. So, what it implies is that all these inequalities actually are equalities. In particular, let us look at this inequality involving the integrations of f with respect to the individual measures mu n. Here we first claim that the limit agrees with the lim sup. So, therefore, here we will actually have of integrations of f with respect to the individual measures mu n. But now, we observe that this is actually equal to the integration of f d mu, which we wanted to prove. So, therefore, this limit exists and equals this. This is the sixth statement, and this we have proved as a application of the equivalent statements 7 and 8. We started by showing that the third statement implies the equivalent statements 7th and 8th. We have now shown that the equivalent statements 7th and 8th implies the sixth statement. But now, what we are going to do is to connect the sixth statement together with the third statement. Let us see. So, we are going to claim that actually the sixth statement implies the third statement. Why? So, in the sixth statement we are asking for bounded measurable functions which are mu almost everywhere continuous, and for that we want the appropriate limit to hold. That limit should be integration of f with respect to the limit measure. But now, in the third statement we are just working with bounded and continuous functions. So, this is a smaller class than that is considered in the sixth statement. So, therefore, immediately we end up having that the sixth statement implies the third statement, and as a consequence we now have this chain of implications is that we combine note 4, note 5 and remark 3. So, we have third statement implies the equivalent statement 7 and 8, which in turn implies 6, but which further implies 3. So, therefore, all these statements have to be equivalent. But recall from our earlier discussion that we have shown that third, fourth and fifth statements are equivalent, and that was clubbed together as a group of statements which is group C. We now have seen that the third statement is further equivalent to sixth, seventh and eighth statements. So, what we do is that we enlarge the group C of statements by saying that from third statement to the eighth statement all these statements are equivalent, and we put them together in group C. So, let us see. So, we are now defining our group C, we are just enlarging it, and from third to eighth statements all of these statements are equivalent. So, we now have 3 groups of statements and we now want to compare between the groups. So, we first state a important result, so the proof for which will be discussed in a later lecture. So, this is the Skorokhard's representation theorem, which says that let us say I have a sequence of probability measures mu1, mu2 and so on the real line together with the Borel sigma field, and suppose mu is another probability measure such that mu n converges to mu in the weak convergence sense. Then the theorem states that we can actually find a specific probability space omega f p and some explicit random variables on this probability space, call them x, x1, x2 and so on, such that they have these properties that x has the law mu, xn's have law mu n for each n, and moreover this sequence of random variables, all of which are now defined on the same probability space. For this, the pointwise convergence actually holds, and the pointwise convergence is for all points on this space capital omega. So, this is a interesting representation of our weak convergence, that we can visualize it as pointwise convergence of random variables on some probability space. So, that is the statement of this theorem. So, we shall discuss the proof of this in a later lecture, but we use this in order to show that the first statement implies the third statement. So, here what is the first statement? The first statement is involving the pointwise convergence of the corresponding distribution functions, but only at the continuity points of the limit distribution function. And the third statement involves the limit of integrations that we have been discussing, that should be equal to the integration of f with respect to the limit probability measure mu, but this should hold for all bounded and continuous functions. So, by assuming 1 we want to prove 3. So, to do that we start by looking at a bounded and continuous function on the real line. Now, we are assuming that the corresponding convergence holds for the distribution functions, and therefore, the sequence of probability measures that we are working with converges in the weak sense to the limit measure mu. Then we appeal to our Skorokhard representation theorem and construct some probability space, and where the corresponding sequence of random variables converge pointwise. But if you have a continuous function on top of that, then the same convergence will be retained. So, therefore, for all points on that space omega, we have the pointwise convergence of this sequence of values. But now, since f is also assumed to be bounded, what we have is that we can appeal to the bounded convergence theorem and look at these set of equalities. So, we start by looking at integration of f with respect to these measures mu n, and let n go to infinity. We want to look at the limit of this. Now, we change variables and bring in the fact that x n now has law mu n, but x n maps from omega f p to r b r mu n here. So, mu n is actually p compose x n inverse. So, that is what we are using here. Now, if you change variables, we end up with this integration over the set omega with respect to the probability measure p. So, this is just changing variables and changing corresponding measures. And therefore, here what we observe is that we actually have the pointwise convergence. Moreover, all the functions are actually bounded. So, therefore, we actually have that this limit exists and equals the integration of f x omega, that function, with respect to the probability measure p. But now, again change the measures, you write it as an integration of the function f over the real line with respect to the probability measure p compose x inverse, which is nothing but the limit measure mu. So, therefore, we ended up showing that for all bounded and continuous functions, the corresponding integrations with respect to the measures mu n converge to the integration involving the limit measure mu, and this is exactly the third statement, and this is following from the first statement by using the Skorokhod representation theorem. So, now this implication 1 implies 3 has further applications. So, the first thing is that this 1 implies 3 was actually a missing part that was used in the proof of Levy's continuity theorem that was discussed earlier in theorem 6 of week 6. And here what we recall is the Levy's continuity theorem actually told us that the first and 14th statements were equivalent. Now, that proof of theorem 6 is now complete because we have the missing link. Now, this missing link 1 implies 3 has been proved using the Skorokhod representation theorem, which we shall prove in a later lecture. Now, what we observe further is that since 1 implies 3, we can now compare between the groups of equivalent statements. So, recall first that group A, which we discussed earlier, involves the equivalent statements 1, 2 and 13. Group C involves the equivalent statements 3 to 8. Since 1 implies 3, what we conclude is that group A of statements implies group C of statements. We now recall further important results from basic real analysis. So, if you have a open set in the real line, check that the indicator function, indicator of G, is lower semi-continuous. Moreover, note that these lower semi-continuous function indicator of G that we are looking at is actually just 0 and 1 valued. So, therefore, this is also bounded. Similarly, we can start with a closed set and look at indicator of the closed set. So, the property that we are asking here is that this indicator of closed sets should be upper semi-continuous, and moreover, since it just takes the two values 0 and 1, again this is bounded. So, these properties are left as exercises for you, please check this. So, let us see some applications of these exercises. So, here as a consequence of these exercises, what we are going to show is that the statement 7 implies statement 9. Now, let us recall what these statements were. So, statement 7 involved certain inequalities for bounded and lower semi-continuous functions, but now statement 9 involved the sizes of certain open sets in real line. So, in statement 9 we want to prove an inequality involving sizes of the open sets G. Now, here if we assume the statement 7 involving bounded lower semi-continuous functions hold, then by taking any open set G in the real line, we look at the corresponding bounded and lower semi-continuous function, which is indicator of G. We then appeal to statement 7 and look at this inequality. We just take this specific bounded and lower semi-continuous function, and that is going to give us the exact statement that we want. So, this is the 9th statement as we get immediately. So, this is just following from the observation that indicator of G is bounded as well as lower semi-continuous. So, therefore, we have that statement 7 implies statement 9, but as a consequence we now compare the group C of statements with group B. So, here in group C we have the equivalent statements 3 to 8, and in group B we have the equivalent statements 9 to 12. Now, if 7 implies 9, we actually are going to get is that group C of statements implies group B of statements. And finally, what we claim is that the 11th statement implies the 13th statement. So, here again recall what was the 11th statement. So, the 11th statement involves mu continuity sets, where the measure of the boundary is getting 0 measure. But here what we want is, for such all mu continuity sets, we want the limit of the measures of such mu continuity sets should go to measure of A. If we have a real number x such that measure of this singleton is 0, immediately we will get that this interval, which is now our choice of set A, is a mu continuity set, because this set has boundary which is only the singleton set x, and therefore, it is a mu continuity set. So, therefore, if 11 holds, then the same statement holds in particular for such intervals where the boundary point has measured 0, and therefore, this is exactly the 13th statement as was pointed out in the list of theorem 3 that was mentioned in week 6 earlier. So, now as a consequence, we now have that the equivalent statements 9 to 12, which includes 11th statement, implies the equivalent statements 1 to 13th. So, therefore, we have now shown that group A will give you group C, and then group C implies group B, and finally, group B implies group A. So, therefore, all these statements are now finally equivalent. So, we combine everything, and therefore, we have the equivalences between now statements between 1 to 13th. So, all these statements are now equivalent, and just to recall, we already have pointed out that the first statement and the 14th statement, that is as part of the Levy's continuity theorem, are equivalent. And therefore, we have now completed the proof of all the equivalent statements that was mentioned as part of theorem 3 of previous week. So, now we have all these different ways we can think of the weak convergence. So, now since we have a explicit proof and we have a better idea of this notion of weak convergence, what we are going to do is to look at further properties of weak convergence and discuss interesting examples. So, this is what we will do in the next lecture. We stop here. Thank you.